Let's continue the ZEUS training, Section 14, Gust Loads. So the Gloads module computes the transient response due to gust excitation by invoking the time domain unsteady aerodynamic computation. And as an option, a static aeroelastic trim solution can be used as the initial flow condition for the gust loads analysis. And the transient responses that can be selected for output include the grid point displacement, velocity, and acceleration, the sectional loads, the grid point forces, modal coordinates, element stress and strain, etc., and the forces and moments at the structural degrees of freedom in terms of Nastran force and moment cards at critical time steps can be exported for a subsequent detailed stress analysis. So let's go over the discrete gust module that we have in ZEUS. So the frequency domain gust analysis is formulated based on the elementary gust solution due to the sinusoidal gust. And the sinusoidal gust is given here, e to the minus I omega times x minus x naught over v, where x is a point on the aerodynamic surface mesh. Now, based on linear theory, the elementary gust solution capital Y of I omega can then be obtained as shown here, where y is equal to q infinity over v times h of I omega times e to the minus I omega times x minus x naught over v, where h of I omega is the aerodynamic transfer function. And the response due to an arbitrary gust profile is then obtained by a superposition of the elementary gust solution. Now, the Euler solver in ZEUS requires a time domain discrete gust boundary condition because of its nonlinear time accurate computational scheme. Now, if we take the inverse Fourier transform of e to the minus I omega of times x minus x naught over v, reveals that the time domain sinusoidal gust is a traveling Dirac delta function. So it's just delta of t minus x naught over v. Now, for an arbitrary gust profile wg, the time domain induced angle of attack is just alpha of t equals 1 over v times wg of tau, where tau is equal to t minus x naught over v. This gust-induced angle of attack is added to the boundary condition of the Euler solver to generate the time domain aeroelastic responses due to gust excitation. So visually what we have here is a traveling delta function shown here. So it sweeps by and hits the wing, and we compute the response due to that gust. So these are the bulk data cards we have for the Gloads input. We have the Gloads card itself, which then calls out to the dgust card to define the gust parameters, and then we refer to the MLD trim, MLD time, MLD print, and MLD stat for setting up the remaining analysis parameters. And then once again, to compute the inertial loads, it's required to import the gset mass matrix using the assign matrix command. So we can import the MGG matrix and we give it the matrix name MGG. And then we have the plot time card, which can be used to output the animation of the deformation and then also the Nastran force and moment cards at a set of time steps. And this is the bulk data in a relationship for the transient gust loads analysis. So we have the Gloads case control command, which refers to the Gloads bulk data card. The Gloads card refers to the flutter card to define the aeroelastic system. We refer to the dgust card to define the discrete gust profile. And then same as the mloads, we can reference the restart, MLD stat, MLD time, and MLD print. So this is the Gloads card. We have the ID number. Con ID is not used. Once again, that's left over from Zero, whereas ZEUS does not allow you to model a closed loop control system. Then we have the Flut ID, which refers to the flutter card. The restart field refers to a restart bulk data card to allow you to restart an analysis. States refers to the MLD stat card, which can further refer to the MLD trim card. ID gust refers to the dgust card. In addition to the dgust card, as an option, you can also refer to the MLD command card. So in this case, the ID numbers of your dgust and MLD command bulk data cards would have the same ID. So in this case, the total disturbance would be a superposition of the discrete gust and the pilot input command. Then we have the time field refers to the MLD time card, and MLD print refers to the MLD print card. Now, prior to the Gloads analysis, a static aeroelastic analysis is performed first to obtain the mean flow solution. And so those parameters are set up in the MK param card. You can use the plot CP card to visualize the CP, and then you can save or retrieve the steady flow using the ST flow card. As the other option is you can start with a trim solution by retrieving that trim solution by the MLD trim card. So in this case, the static aeroelastic analysis will be skipped. And then once again, if you want the loads, you need to import the MGG or the MGH matrix. Next, we have the dgust card to define the discrete gust profile. So we have an ID number, and then next we have type, which is a character string to specify the type of the gust profile. So type can be step, pulse, sine, OMCOS, which is 1 minus cosine, random, or table. So for type step, the gust is a step function representing a sharp-edged gust. For type pulse, we have this type of excitation where when tau is greater than or equal to 0, then it's given by e to the minus lg times tau squared. For type sine, we have a one-cycle sine wave between times tau is 0 to lg. For type 1 minus cosine, we have a 1 minus cosine gust profile. Moving on, for type random, the gust excitation is a random number between -1 and 1 when tau is between 0 and lg. And then for type table, we have an arbitrary gust profile defined by the table D1 card. And then lg is either a real number or an integer defined in the equations shown above in the type. So for the pulse, sine, 1 minus cosine, and random, lg is a real number. For type table, lg is an integer referring to the table D1 card to define the gust profile. WGV is the gust velocity divided by forward velocity, which represents a scale factor to the gust profile. So you as the user must calculate this value and put it in the card. And then x naught is the streamwise location relative to the origin of the aerodynamic model for the gust reference point. So here's a diagram illustrating how the discrete gust profile is set up. So for this example, we have an arbitrary gust profile defined by the table D1 card. So our x naught here is where the reference point of the gust starts. So our origin is at the nose in this particular model. Then we have x naught, and then we have this gust profile.